I want to remind you of what differential equation we're dealing with. We're dealing with a second order differential equation. And the differential equation could be of this form. And normally we would want to write it in standard form to assess the trouble points, the singularities they call them. And so we want to
What does it mean, analytic at x0?
analytic means you can take an infinite number of derivatives. But the formal definition that they give in the book is analytic means that you can find a power series around that point that has a radius of convergence that's bigger than 0. So analytic are nice points, and a singular is something that's not nice. Now, if it's not nice, it could be really nice enough or really bad, not nice. So a singular point can be a regular singular point if it's not nice but could be nice enough for us to deal with. Or it could be an irregular point, which is not something that we're even going to consider. All right. So in this section, this is section 6.3, we're going to consider regular singular points. So points that are not analytic, but they satisfy some condition that's easy enough for us to deal with. And if you remember last time, the condition has something to do with creating a little p. So what we did last time was we had this big P over here, capital P, and we created a little p. Let's see if I can write it like a little p, which is equal to capital P. Well, yeah, I'll just put capital P divided by x minus x naught. And then there's little q, which is capital Q divided by x minus x naught squared. So if these are both analytic, these new functions that we would create are both analytic, that means we can make a power series around that. Not only that, but it's called a regular singular point. Yeah. Oh, yeah, they're multiplied. Sorry. This would be x minus x naught multiplied with capital P of x and x minus x naught squared q of x. So what this is basically saying is that if you have, if p of x happens to have a denominator that probably has something to do with a sub 2, it has a denominator of this with a factor of x minus x naught or x minus x naught squared or something like that, then this little p of x would wipe that out, and then it would become analytic, and then there would be no bad denominators. So this is our big theorem. Our big theorem is due to this guy, Frobenius, which allows us to find a power series solution. It's not a regular power series solution. If you remember a regular power series solution, it's just going to be this thing inside here. But Frobenius says that if we are able to multiply this by some power of that factor, x minus x naught, and if we can get this to work, or we can get this to work, we should be able to find a power series solution. Okay. The tricky part about this is finding R, and last time I wanted to do a problem, but we don't have enough time to kind of develop this idea of finding R. So instead of trying to develop how to find this R, what we're going to do is we're just going to tell you how to find the R. There is a formula or a special equation that helps us find the R. And that it's kind of like when we did second order with constant coefficients, and then we have this what's called the auxiliary equation. So there's something similar to the auxiliary equation for Frobenius' theorem, but they actually call it indicial equation. Okay, so Frobenius theorem is a power series that introduces another variable R, and then what we need to do is we need to find that R. Now, after finding that R, we're going to break this up to different cases again, and then those different cases are going to depend on what R is, and then that'll help us find our solutions. So, the equation that I was trying to refer to is called the Indicial Equation. And for this time and for the rest of our discussion, probably should have just kept our discussion with x naught equals 0, since that's all we're going to consider anyways. So instead of looking at x minus x naught, we're just going to look at x minus 0, which is just x, as our point, or x is equal to 0 as our center point. So the indicial equation depends on having us come up with a power series of little p of x and little q of x. Okay? Now, you think, wow, we're already trying to find power series solutions. Now we have to come up with power series solutions and stuff like that. Well, in this case, the power series solution, the power series that we need, we really only need a little bit of it. Actually, we only need one term from each of the power series, and we only need the first term for each of those power series. And what that's going to do is that's going to make it easy for us to, I mean, a lot of these things will end up being polynomials anyways, and all you're interested in is looking for the constant term. Okay, so that's what we're interested in. After you find the constant term for those power series, you're just going to put it into this equation and then solve for this quadratic equation R, solve for R. Okay? All right, so for this, before we move on, maybe we could do a quick example of finding the indicial equations. And this is one of the first equations we're going to look at, a differential equation. So let's do an example real quick. So our example is going to be x squared y double prime plus x y prime plus another x squared y is equal to 0. So what we'll do in this page is we'll find the indicial equations, and then I'll do another quick example, find the solution for the indicial equation, and then we'll try to solve for those two differential equations. So if we identify our values that we need to identify, or our functions themselves, the first thing we want to do to get our p and our q, capital P and our capital Q, is to write this in standard form. So let's divide everything by x squared here. We got y double prime is equal to, oops, not equal to, plus x divided by x squared, right? Times y prime, plus, and then x squared divided by x squared, so that's just a 1, times y is equal to 0. So we got capital P of x and capital Q of x identified. From here, we come up with trying to find out what P, little p of x is. And that is x times capital P of x, which is just 1. And this is a constant already, and so we don't have to find a Taylor polynomial or power series for this. It's just that. That's just it. And in terms of lining this up with all these constants, this is really, this is a sub 0. Or if you want to put it this way, this is the power series that you would expand it to, and then you would identify a sub 0 as that first term, the constant term. Now P, well, we have P. Now Q of x is x squared times Q of x, which is just 1. And if we imagine this, again, like a power series, we can pretend that we're expanding it as a power series and then identify your b sub 0. And that's really all we need to do is identify the b sub 0. So b sub 0 is equal to 0. Any questions so far? So now that you know that, our equation, I don't know if I should call it IE. So our indicial equation is going to be r minus 1 plus a sub 0, which is 1 times r, plus b sub 0, which is 0, is equal to 0. And if you solve for r, what's r equal to? R is equal to 0? Okay? Is that good? All right, good. So I'm going to do another example. I don't know if I want to stick with this particular theme. This particular differential equation has a special name that we'll give it later on. Let's stick with this special differential equation. X squared y double prime plus x times y prime plus x squared minus alpha squared y is equal to 0. So it's essentially looks like it's the same differential equation. But let's see how this works out for us. We're going to write it in standard form by dividing by x squared again. So we have y double prime is equal to, again, it's 1 over x, not equal to, sorry, plus 1 over x y prime plus x squared plus alpha squared divided by x squared times y is equal to 0. Maybe I should put an actual number for alpha. All right, let's hope it works out for us. So From here, I want to identify my A naught and B naught. For me to be able to identify my A naught and B naught, I want to be able to write the power series for p, and little q. And for me to be able to find the power series for little p and little q, I need to identify capital P and capital Q. So little p is equal to x times capital P. That looks like it's the same thing, which is going to be 1. So our A naught is equal to 1 again. Our little q is equal to x squared times this x squared alpha squared, x squared minus alpha squared over x squared. Well, the x squareds cancel, and I just have x squared minus alpha squared. Wait, let me rewrite that as a power series where I have the constant first and then a linear term. Oops, this is a minus, shouldn't be minus. Constant, a linear term, the quadratic term, which is 1 times x squared plus, and then zeros from here on out. So by doing this, I can identify my my B naught. That's my constant term for this power series expansion for little q. Okay? Then this would be something with an x cubed in there. No, because we're only concerned about when we're finding the indicial equation, we're only concerned about the constant term for that little p and little q. Because this is your little q of x, and I just wrote it so that my constant term was first, my linear term was second, my quadratic term is this, which is 1x squared, and then everything else is not there. Okay, if this turns out to be an ln or a tangent or a sine function or something like that, then you would need to find a power series for that. And then really all you want is that first term for both of these power series. Okay, good. All right, so our equation that we're looking for is going to be r minus 1 plus your A naught, that's 1 again, times r plus your B naught. In this case, it's minus alpha squared is equal to 0. So if we solve for this, so r is plus and minus alpha. Okay? So these are quadratics, so we really should have 2 roots, right? And then we know the rule for quadratics. The roots are either distinct real roots, complex conjugates, or the same root, the same real root, but with multiplicity too. I think it should turn out that we should never come up with a complex conjugate pair here. So we're only going to have the 2 possibilities. It's either the same root or 2 different roots. And so if you come up with complex conjugates, then you might have done something wrong. Okay, so now that we know that piece of information, or for these 2 particular differential equations that we're working with, Let's take it to the next step. What are we going to do after we find our roots? So it turns out that finding those roots will help us determine what kind of solutions we're going to get. And for this, remember, you're not going to have any complex conjugates as a possibility here. You shouldn't. And so we have two possibilities. Actually, we're going to have three different cases. Why? Because that's what they say. So the three cases all revolve around having two real roots or having one root that repeats. So case one is a two real root possibility. But the way they break down these cases depends on the kind of solution that we're going to get. So the first one, we have two distinct roots, but the difference of the two distinct roots is not an integer. So apparently that makes a difference. Okay, so if the difference between these two distinct roots is not an integer, then you're going to have two linearly independent solutions. One of them looks like this. With one of the roots, and the other one is going to look pretty much like it, except you'll have the different r for your other root. Remember, these r's come from multiplying how many of these things we're going to multiply the power series by to continue to get a power series. That's what those r's are coming from. And it's going to turn out that, well, those r's might not be whole numbers. You might have fractions for them or something, in which case, well, there's weird things that can happen. All right, case two is, again, the distinct root case for your finding your roots. But if they are integers, then one power series might look just like the other power series, except, you know, they're off by a power of x. So if you're off by a power of x, it's just like multiplying by x or multiplying something by x. But if it's an infinite series, then multiplying something by x is going, they might give you two linearly dependent solutions. So to take care of the linear independence, what they're saying here is that your second root is going to have an ln of x. So the bad news is that ln of x might be equal to, this whole term might go to 0. And so your solution might look just like the first one. Nothing is definite here, it seems like it. But we're not going to know that until we actually try to do these problems. The third case is when the two roots are the same with multiplicity 2. And if they are, then you're for sure going to have the ln of x there. That one can't go to 0. Like this one could possibly go to 0. Might disappear, in which case then you'll have a solution that you might not be able to find your second solution. But for the third case where the repeated roots, then you're definitely going to have the ln of x. Oh, that shouldn't be there. I was copying and pasting. It happens. Okay. All right. So I'm sure this is pretty confusing and looks really difficult. And I'd like to say, let's do an example. I'll clear things up, but I'll do an example, and it'll just be as difficult as it seems. All right. Whew. Let's try to do an example. I don't know why, but I think I'm going to start with a third case, because that's the first differential equation that we wrote down on the previous page. So all right, let's take a look at our differential equation, first example that we're going to work on, and hopefully this doesn't take the rest of the class. This is our differential equation. We saw earlier that your roots are 0 and 0, right, from your indicial equation. So we can say that we are looking at case 3, where you have the two roots are equal. And so what we're going to do is we're going to first try to find out our first y1, our first solution. Okay, Frobenius tells us our solution, I'm going to say y, but this is like y1. This is y1 that we're looking for. Our solution should look like this. Okay? So this is from Frobenius' theorem over here, where x naught is equal to 0. And like I said, all the problems we're going to do is going to be x naught is equal to 0, so we don't need to mess with it. So that's how we begin. Now, since we did find our solution to our indicial equation, we found a value for r, and since r is going to be the same here, r is equal to 0, then we can just knock this r off, right? So it'll just be, it's almost like just working with a regular power series. So that's what we'll do. We'll treat it like it's a regular power series. All right. So with a regular power series, we have a value for y. We need y prime and y double prime. We used to do something when we took derivatives of power series. When we took derivatives of power series, we just knocked the other one out and say, that doesn't matter because it's equal to 0 anyways. I guess in this case, since r is equal to 0, that's also going to be the case. But normally, we want to keep the index the same, because in case r was not equal to 0, we have a k minus or k plus r here that we would put down as a coefficient. And this would be k x to the k plus r minus 1. And when we're dealing with r's, especially r's that are negative or fractions, we're not looking at regular power series anymore. We're looking at just power functions, but they're not power series because power series needs to have the powers of x as positive integers, and in this case they're not necessarily. Our case will still be positive integers. So, but when you're doing Frobenius' theorem, when you take your derivatives, you should keep the k is equal to 0 here. Is that clear? Maybe it'll be clearer later when we do our next one. All right, so our y double prime is going to be equal to the sum. Again, let's keep k starting from 0 to infinity. We have k minus 1, ck, x to the k minus 2. Okay. All right, so we'll put them in here. We got an x squared multiplying with the y double prime. So the x squared being multiplied here will just give us an x to the k power. So I'll just put that together. You got k minus 1, ck, x to the k power. Plus now the y prime is going to be multiplied by x, and so I'll add 1 to this x over here, so it'll just be x to the k again. Now the third one is going to have to be multiplied by x squared, so that's going to give me 2 extra x's for my power series. So this is ck x to the k plus 2. So now I've gotten our, according to Frobenius, we're going to use this as our solution. We took the derivative once and twice, and we put that back into this equation. And I guess now we can for sure, because r is equal to 0, we can start these indices appropriately. Like this one really starts at 2, right? Because when you put 0 in there, you get nothing. And so in terms of matching the powers, I'm interested in matching the powers here. I have x to the k for 2 of them, and this is k plus 2, so I want to shift this index. So I'll do a couple of things in this step. This is not a shift. This is considering k is equal to 0 is 0, k is equal to 1 is 0, so there's no contribution, so it starts with k is equal to 2. I suppose I could have found that later on too, but this stays the same basically. This, when k is equal to 0, it will have no contribution, so I'll just start my series with k is equal to 1. And now this is the one with a shift, k. I need to subtract 2, right? So my index starts at what? Starts at 2, goes to infinity, and subtracting 2, I get k minus 2. Subtracting 2, I get x to the k. Now I have matching powers. I can put it all together. Is that okay so far? All right. So they're almost all aligned here except when k is equal to 1. So I'm going to make a special case when k is equal to 1 here. That'll give me 1 C1 x to the first power. Everything else now I can put into one summation sign. That would be k minus 1 ck. I probably have to do a little bit more simplifying here afterwards. K ck plus ck minus 2 times x to the k. So let's see if we can simplify the constant, the coefficient inside of the summation sign. I have a ck that I can factor out. How's this going to work? Just tell me what the answer is. This is k squared? Is it just k squared? No. K squared, right? Is that right? Wow, okay. I guess that's good. So, what do we have? We have a bunch of things that are going to be set equal to 0. So, it looks like from the beginning here, C1 is going to be equal to 0. And this recurrence relationship that we're going to find, this relationship looks like it's going to be a relationship between, for k bigger or k is equal to 2 and higher, I'm going to get ck is equal to, if I set this equal to 0, I bring the ck minus 2 over to the other side, so that's negative ck minus 2, and then I divide by k squared, and I get this. Because of each of the coefficients are going to be equal to 0, and I have this coefficient sitting out by itself. And I would set that equal to 0, and I would set these coefficients in here equal to 0, and this is what I got. So C1's equal to 0. Now, if ck, this is good for k, equals 2, two, 3, 4, etc. So when k is equal to 2, I'm going to have negative C0 divided by 2 squared. I'll just put 2 squared for now. Is that right? That looks right. When k is equal to 3, this is equal to negative C1 over 3 squared. And what is C1 equal to? C1's equal to 0, so that's gone. C4, when k is equal to 4, this is negative C4 minus 2, negative C2 divided by 4 squared. What's that equal to? This is equal to positive C0 4 squared times 2 squared. Right? Is that right? And C5 is what? 0. C7 is what? C9. So all the odd C's are gone because of C1. And let's see if we can find, well, I suppose we can try to express this in general terms. Let's do one more. C6 is equal to minus C4 divided by 6 squared. So that's just equal to minus C naught. And then 6 squared, 4 squared, 2 squared. Is this looking, it's not looking, can we find a pattern here? That would be nice if we could. It kind of looks like there should be a pattern. Maybe one more. Wait, can you tell me without going through the process what C8 is going to be? Positive or negative? Positive C naught. Why? Because it's negative, positive, negative, positive. So it looks like it's switching off. And then what's down here? 8 squared, 6 squared, 4 squared, 2 squared. All right. Sure. Yeah, so what if we factored out a 2 from each of them? Let's see if we could do this. Let's do it for this one. Minus C naught. We factored out a 2 from here, a 2 from here, and a 2 from here. Oh. So it'll be 2 to the to the 6th power? 2 to the 6th. And then what do we have left? 3, 2, 1. Well, because we took out 2 2's from each one, right? Or did we just take 1 2 out? So is it still, so is it n factorial squared? Say it again. Well, let's use the 6 first. So is n 6 or n 3? So I want 3 factorial. So let's just say 3 factorial. I don't want n's right now. I don't want n's right now. So this one will be 3 factorial. Is this 3 factorial going to be squared? It's going to be squared. Now, how many 2's did we take out? So 2 to the 6 times 3 factorial quantity squared is exactly equal to this. Is that what you're saying? So if I go to the next one, this is going to be positive C naught, and this would be 2 to the 8th, 4 factorial quantity squared. And does that match up? Is that correct? Okay. So instead of going to n over 2 factorial, because that makes things kind of look messy, what if instead of, since we know that we're only going to be dealing with even numbers, right? Why don't we just change the subscript into n, 2n? Did it change colors? So let's try to see if we can write c sub 2n is equal to, now I have a alternating series, right? So the first one is when n is equal to 0, this should be positive. When n is equal to 1, I have c2, and this should be negative, right? So this should just be n. Is that correct? It's either n or n minus 1, or n. It's either n or n plus 1. So I think it's n. Tell me if it's wrong. Okay, so we'll move on. We got the c naught. And then we're dividing by, now this is going to be 2 to the same power as the subscript, 2 raised to the 2n. And then now we can write the factorial without the denominator. It'll just be n factorial quantity squared. No, because we switched the subscript. Okay? All right, so we got the constants. Now let's put it back into the power series. The original power series looks like this, and we've determined that all the odd terms will disappear. So we can just write our term like this. So our power series y is going to equal to negative 1 to the n c sub 0. Wait, that's constant. I can just take that constant out, right? Because all the terms are going to have the c sub 0. So why don't I take that constant and move it on out? Divided by 2 raised to the 2n power n factorial quantity squared times. So this will be a power series times x to the nth power. It has to be matching with the same subscript, right? So it'll be 2n, x to the 2n. And all the odd numbers disappear, so this is just going to list down all the even functions. Ah, cool. I think we did it.
Where did the R come from?
Say it again?
Where did the R come from?
The R came in at the very beginning when R is equal to 0, when we did the indicial equation. All right. So this is y1. What's y2 equal to? Yeah, y2 plus another b. Oh, what's the other b? Well, all right, so we have some bad news. The bad news is that to find this next solution is going to be almost as much work as we found the first. It's not as easy as putting this, slapping this together, because the b is going to still be unknown. So let's see if we can find a second solution. What? That's when r is equal to 0. All right, let's do this. Let's do this. Let's just buckle down and do it. All right. Yes, new page.
So the homework should have like one problem, right?
So this is continued. We found a solution. Y1 is equal to, let me ignore the C naught for now. N goes from 0 to infinity, -1 to the n over 2 raised to the 2n times 2 factorial, or n factorial, squared times x to the 2n. That's our first solution. We should be proud of that. Our second solution is going to equal to our first solution times ln x plus another series. Yeah. We did, but I'm just going to ignore that, and I'll tack on the C naught if I finish this problem with a general solution. All right. So this one, B naught, or I'm sorry, BK. All right. Now this is our second solution. Now our second solution should satisfy our differential equation. Sounds like a rap. I just have to make it rhyme. So we need to take the first and second derivative again so that we can plug it into the differential equation. Oh boy. All right, let's see. Y2 prime. Oh boy, this is a product rule, right? So derivative of the first times the second plus the first times derivative of the second. And the derivative of this is the same derivative that we've been doing with power series in general. And since r is equal to 0, well, I don't want you to get used to putting a 1 here. I would put a 1 there if this was an ordinary point, but since this is a regular singular point, we really should put 0 in there in case r, if r was not equal to 0, then you're going to have different problems here, and your problem is not power series anymore. So I'm going to keep it at 0, but when I start doing the work, it'll end up becoming 1. And it's only going to change because r is equal to 0. I keep stressing that because I kind of got you guys used to changing the index already in your derivative. But that only works if you have a regular power series. This is a regular singular point. All right. K, bk, x to the k minus 1. And now the second derivative, I might need more space here. Derivative of the first times the second plus the first, derivative of the second, plus now another product rule, derivative of the first times the second plus the first times derivative of the second. So we got two product rules. We end up with 4 terms, and then we got another derivative here. K goes from 0 to infinity. K minus 1, bk, x to the k minus 2. All right? Now, let's multiply, what? Yeah, bk. Okay, now let's multiply this whole thing, y2, with x squared. Boy, is that going to be easy? Yes, that's going to be a piece of cake. It's not. I'm just pretending that it's going to be easy. So this is an x squared here. Oh, multiplying this with an x squared, it'll get rid of that one of the x's, so this would just be x times y prime. Because this sub 1 is this first function that we found. And so technically the y should have a sub 1. It's a solution that we already know works for the differential equation. All right, so the next term is done. The next one also will disappear. Oh, this is the same one, right? And here it's a negative, and the x squared all goes away, so this is just y1. Is that right? Okay. Oh, plus this stuff. So you multiply this by an x squared, it'll just be the sum of the coefficient, k times k minus 1, bk, and then now it's just x to the k. Let's lasso all these things and remember that this is x squared y double prime, y sub 1 double prime. All right. Now let's multiply this y2 prime with x. Yeah, we're putting the y sub 2. These are going to be y sub 2s technically. Oh, yes. All right, now let's multiply this by x. This will be x y1 prime ln x. That's the first term times x plus y1, no prime, and then x, and x will disappear, and then that's it. And then x times x to the k minus 1 is just x to the k. Okay. And then finally I get this last one. I got x squared times y2, so x y1 ln x plus the sum k goes from 0 to infinity of bk x to the k plus 2, because I had to multiply it by x squared. Oh boy, just getting warmed up. Let's see. I'm interested in the ln's. Let's use a highlighter for that. These terms have an ln in them, so I'm going to put them together and factor out the ln. What do I get? I'm going to get x green. I'm going to get x squared y1 double prime. Ln is going to be taken out. Plus x y1 prime. Ln is going to be taken out. Plus, oh, this should be an x squared. Plus x squared y1 okay. Yeah? Why? This is our original differential equation, and we said that y1 is a solution to this differential equation. So if y1 is in fact a solution to this differential equation, then yes, this is equal to 0. Okay? Now, let's see more things disappear. Like a positive and a negative. Anything else disappear? That's it? Oh, man. All right, so that's gone. What do we have left? Now we have two of these. So let's say that's taken care of. So what's left? What's left is just all our summations. Oops, not equals. Plus. Can we put this together? Let me just rewrite it first. K goes from, can I just start this from 2 to infinity, k minus 1, bk, x to the k, plus, I'm going to start this with 1. K goes from 1 to infinity, k, bk, x to the k, and this is the one with a different power. So that's the one we need to change the index on. And this is supposed to be equal to 0. All right, so we can knock off this ln, and now we have this thing. Let's see if we can put this together. It's exactly the same thing that we had earlier, right? So let's see if I can. Well, let me write it carefully. K minus 1, bk, x to the k, plus this sum starts at 2, this one starts at 1, k, bk, x to the k, and then this one, after a shift, this one can start at 2, and we have bk minus 2, x to the k. So it's the same as the one we had before. The only difference is we have this other term out here. So let's put these two things together. or these things together, we have a, when k is equal to 1 is our business, remember? b1 x to the first power. And then after that we have k starting from 2, and this we can put all together in one summation. And what you're putting together is these two added together, so that's just k squared bk, right? And then we have a plus, and this one is not the same as bk, it's bk minus 2, so we can't combine that. So where's x1 prime? Oh, it's right here. Let's find x1 prime, or y1 prime, sorry. This is y1. We're going to need some y1 prime business so that we can put it down there and see if we can get anything out of it. Y1 is equal to this. If we want to take the derivative, y1 prime, that's equal to n goes from 0 to infinity, -1 to the n. These are all constants. And the derivative here is just going to be 2n, and this is x to the 2n minus 1. And when n is equal to 0, it turns out that this thing goes away, so we can really just start this when n is equal to 1. All right. Now let's take that down here and multiply it by 2x. So 2x is a constant. N goes from 1 to infinity, -1 to the nth power. 2, let's call it 4. 2 to the 2n power, n factorial squared. And now there's extra x here that I add on, so x to the 2n minus 1 times x is x to the 2n, so we're back to x to the 2n. This is 2 to the 2n, yeah, that didn't change. If we want, we can keep it like this for now. Boy, maybe I should just give you the answer. Yeah, I have -1 minute. Anyways, so maybe we'll just put ... here. I do want to highlight this particular solution here and the solution that we're about to get that we didn't get. These are actually well-known series. These are series that you probably should know when you guys are working as engineers or physicists or whatever you're going to end up doing, or math people. At some point, somebody's going to say, have you heard of the Bessel function? This is a Bessel function of order 0, and that's what we're deriving right now. A Bessel function cannot be defined with an actual function. a Bessel function is defined as an infinite series. In fact, it's the series that we're working out. And what's important about that is the Bessel function is a solution to this particular differential equation. Okay? So next time we'll see about finishing this up. I might just do a recording and just have you look at it. But this is an important function for you to try to remember, or at least think back to say, hey, I vaguely remember that.
Take a picture.
Take a picture.
That one.
All right.